In the second example, we are given that we have a deformation, a compression in this case, of 3.5 centimeters under a force of 150 newtons. We're not given a direction, so let's assume down. So what's happening here is we've got a spring, and after a force, this is before, and after a force is applied, the spring has been compressed, again because there's a force acting downward, and the difference in length between the original and the final length is 3.5 centimeters. And this is a 150 Newton force doing that compression. So recall that a Newton and a half is about the force you apply to a cell phone to hold it in the air against gravity. This is about the weight of 100 cell phones or so. All right, and so the question asks, what is the K of this spring? So going back to our equation, F equals Kx, this is also known as Hooke's law, we can solve for K. K then equals, let's divide both sides by x to cancel this x. It will end up on the other side as the denominator. K equals F over x. And so we have 150 newtons down, and we can give this compression a direction down as well. 3.5 centimeters. Which equals a K of 42.86 newtons per centimeter. Now, because this compression is also down and the force is down, then the directions cancel, and K, which is not a vector, does not have a direction. And so now that we've talked about a number of different kinds of forces that might act on objects, we can talk about forces being balanced or not. Forces, just like any vector, add as per vector addition that we discussed last day. And so a balanced force, if the forces on an object are balanced, what that means is the sum of all the forces acting on that object will equal 0. So in this case, on this boat, there are two forces acting on it. One, which is the gravitational pull of the Earth. This pulls the boat downwards. The other is the buoyancy of the boat, which comes from the fact that it displaces some amount of water, but the boat itself is lighter than the water it displaces. So the water pushes upward on the boat pushes down on the water pushes upward on the boat. Again, that's Newton's third law. And so, because this boat is not accelerating up or down, we note that the F net must equal 0. Must equal 0. Why is that? Because F, again, equals ma. F net equals ma. And with no acceleration up or down, F net must also be 0. And so, in a situation where we're not experiencing any acceleration, in this case we're just talking about the up and down direction, this could be accelerating to the left or right across the water, but just in the vertical, there's no net acceleration, there's no net force, and we can say that these forces are balanced, or that these forces are in equilibrium. Now, we can say that if we have on an object, this object right here, if there are two individual forces of equal magnitude and opposite direction, then these forces are balanced. So here's a situation where, let's say, gravity is pulling this object down, but the normal force is keeping it from accelerating downwards. So the normal force is equal to the gravitational force. We can tell because this object is not accelerating up or down. There can be, it doesn't have to just be two forces though. For instance, on this object, let's say we have the force of gravity acting down, and let's say as well that someone's pushing down on this box, FA, so there's an FA on that box. And again, there's a normal force. In this case, Fn, pointing up, balances these two forces, Fa and Fg, which both push the box downward. Now, that's not always the case. Sometimes an object can be said to be acted upon by an unbalanced force, which is to say that there's no force to cancel out the first one. For instance, if we try to push an object across a floor, there'll always be a frictional force. However, that frictional force is subject to some maximum, which is dependent on the normal force acting on the object and the coefficient of friction between the object and the surface. And so this can take a maximum value only. And if we push harder than that maximum, I'll draw this arrow bigger to indicate that it's a bigger force, then this frictional force balances only a part of the applied force. So here, this is an object acted upon by an unbalanced force. That is to say, the sum of these forces is not zero, whereas in a balanced situation, the sum of the forces, or the net force, is zero. So in these cases, F net equals zero, because when you add up the two down vectors here and the one up vector, those are the same. Or if you add up this one up vector and the second down vector, then again, you end up with zero. And in this case, F net does not equal zero because this force is larger than that force, even though they're opposite in direction. Now, if we are in a situation where the forces on an object are not balanced, then those unbalanced forces with an F net not equal to zero will result in changes of the state of motion, that is to say, the object will accelerate. So recall that F net equals mass times acceleration. If you can calculate the net force acting on an object, in this case, perhaps you've calculated the frictional force to be equal to 5 newtons, and this applied force to be equal to 17 newtons. We can add these up. Because they're in opposite directions, one will be negative, one will be positive. So in this case, F net will equal 17 newtons. Let's make to the right positive. We can pick that though. This is arbitrary, in that we can make left positive if we want to, but in this case left is negative, so negative 5 newtons to the right. So the 17 Newton force to the right is a positive 17 newtons. To the left, this 5 Newton force is negative 5 newtons to the right. This negative just means it's opposite to the direction, to this direction right. And so doing this, we get 17 plus a negative 5 That's the same as 17 minus 5, 12 newtons to the right. And so let's say that this object had a mass of 5 kilograms. F net equals ma. We can find the acceleration because we have the F net and we have the mass of the object. So acceleration equals F net over mass equals 12 newtons to the right divided by 5 kilograms, and that makes our acceleration equal to 2.4. Now, what do we do with these units here? Newtons per kilogram? That is correct, but if we remember that newtons are equal to kilogram meters per second squared divided by units of kilograms, then our acceleration becomes 2.4 meters per second squared, which is appropriate because those are the units of acceleration. And so here we have unbalanced forces acting on an object. We can calculate the net force, and if we have the mass of the object, we can calculate the object's acceleration. So we calculate the net force in the horizontal to be 12 newtons to the right, the mass being 5 kilograms. We can rearrange this equation to solve for A, and we get 2.4 newtons per kilogram. But if we turn newtons into kilogram meters per second squared, then the kilograms cancel nicely, and we end up with units of meters per second squared. And so, to figure out if the forces acting on an object are balanced or not, we use a free body diagram. And we will do some examples of those on the next video.